Hey everyone, and welcome. Today, we're diving into something called machinability. Now, this isn't just about cutting metal, it's really the science of precision, the stuff that makes the difference between a perfectly made part and, well, a very expensive piece of scrap.
So have you ever wondered about this? Why is it that some materials, like aluminum, seem to cut like butter, while others, like a tough superalloy, feel like they're fighting you for every single millimeter? The answer is all in this wild dance of forces, heat, and friction that's happening right at the cutting edge.
To really get our heads around this, we're going to break it down, kind of like lecture notes. First up, we'll look at the tool's first line of defense, its materials and coatings. Then we'll explore how the actual shape of the tool is key to success. After that, we have to face the inevitable enemy, tool wear. And finally, we'll wrap it all up into a playbook you can use.
All right, let's jump right in with our first big idea, the tool's armor. See, before you even make a single cut, the whole game can be won or lost based on what the tool is made of, and maybe even more importantly, what it's coated with.
So what is a tool coating? Well, think of it like a super thin, high-tech suit of armor for the cutting edge. We're talking incredibly thin here, but it is packed with properties that help it survive the absolutely brutal conditions inside a machine. It's not just about being hard, it's about being smart.
So what does this armor actually do? Oh, it does a lot. It's not a one-trick pony, that's for sure. It cuts down on friction, which stops the material from literally welding itself to the tool. It acts like a heat shield. It makes the surface way harder to resist scratches and all kinds of wear. It even helps you get a cleaner part by stopping those little annoying burrs from forming.
And hey, this isn't just theory. Just look at this data. A team led by Oslu put this to the test on a titanium alloy that's notoriously difficult to work with. And the results? They couldn't be clearer. The aluminum oxide coating, that's Al2O3, just blew the standard coating out of the water. The tool lasted way longer, it took less force to cut, and the final surface was much smoother. It just goes to show how picking the right armor is a total game changer.
Okay, let's move on to our second section. You can have the best armor in the world, right? But if the shape of your weapon is wrong, that armor isn't going to help much. Tool geometry. We're talking the specific angles and curves of the cutting edge. That's where the real physics of the cut happens.
And it's all about trade-offs. There's really no free lunch in machining. Take the nose radius. That's just how rounded the tip of the tool is. A bigger radius can give you a nicer surface finish, but it might also increase the cutting forces. Then you've got the rake angle. The best way to think about it is like a chef's knife. A really sharp, aggressive angle slices through material super easily, which is great for reducing forces. But just like a delicate kitchen knife, it's also weaker and more likely to chip. It's a constant balancing act.
Now check this out, because this is where things get really interesting. You'd think that balancing act is always straightforward, but it's not. A study from Kaya's team in 2023 found that when they were machining an aluminum alloy, a larger corner radius, the one you might expect to increase forces, actually did the opposite. It led to lower cutting forces and a better surface finish. So the big lesson here is that the so-called rules can change depending on exactly what you're cutting.
So, what's the bottom line here? It's that tool geometry is this delicate dance. You need an edge that is sharp enough to slice material cleanly, but at the same time, it has to be strong enough to handle the massive pressure and heat without breaking.
Okay, it's time to meet the villain of our story, tool wear. No matter how perfect your tool's armor is, or how clever its shape is, this is the enemy that never sleeps. It's the slow degradation that eventually stops every single machining job. Understanding it is the first step to beating it. And tool wear isn't just one simple thing. It's more like a whole gang of troublemakers. You've got flank wear, which is when the side of the tool gets worn down from rubbing against the part. Then there's crater wear, where hot chips literally blast a crater into the top of the tool. You've got adhesion, where tiny bits of the workpiece actually weld themselves onto the tool. And finally, abrasion, which is like sandpaper, where hard particles just scratch the edge until it's dull.
So why does all this matter?
Well, this quote from a 2024 study by Sakamoto's team really hits the nail on the head. As flank wear gets worse, it's actually changing the shape of your tool while you're cutting. And that, of course, messes up the whole process and ruins the surface finish of your part. Simply put, a worn tool can't make a good part.
So how do we fight back? Are we helpless? Not at all. We get smart with data. In modern manufacturing, we don't just wait around for a tool to fail. We use sensors to watch the cutting forces, to track vibrations, to even look at the heat in real time. It's all about predicting when wear is getting bad and then doing something about it before it ruins the part.
So, we've seen how coatings give us armor, how geometry defines the cut, and how wear is this constant enemy trying to bring the whole thing down. So how do we put all this knowledge to work? Well, let's pull it all together into a nice, clear playbook.
Here it is, your 3-point playbook. This is really the heart of our lecture notes today. Number 1, select the right armor. That means you have to choose the best tool, material, and coating for the specific material you're cutting. Number 2, optimize the shape. That's that balancing act we talked about, finding the sweet spot between low cutting forces and a strong edge. And number 3, monitor the enemy. Don't just sit back and wait for things to go wrong. Use data to track tool wear and stop it in its tracks. If you can master these 3, you are well on your way to mastering machinability.
And that kind of brings us to one last big question to think about. We're getting really good at this stuff. With smarter AI monitoring and new materials coming out all the time, are we getting close to an age where tool wear is basically a solved problem? A time when perfect machinability with zero mistakes and ultimate efficiency isn't just a dream, but the everyday standard. It's something to think about. Thanks for joining me on this explainer.